you guys learned about the 3 different types of phases, right? You guys should have watched that video yesterday. If you're gone, the paper's over in the box and you guys can grab it. What are the 3 phases? I know it said 4, but we're going to focus on the 3 basic ones. What are the 3 phases or states of matter? What are they? Solid, liquid, gas, okay? And so when we look at a phase change graph, it's about the states of matter. And at different points of this graph shows us where the different states are. Let's look at our graph and what it kind of tells us here. So it tells us here this side is temperature, right? So as we're increasing temperature, we're increasing the speed. We learned that, right? Down here it just tells us how much heat is there. Now, why is the heat, the mass is not increasing, right? But we're increasing in heat. Why are we increasing in heat if we're not increasing mass? What are we increasing as we go to the right? Because what's the 2 things heat depends on? Speed and mass. So if I'm not changing mass, then I'm changing the speed. How do I know that I'm changing the speed here? Because what's changing over here? Temperature. And what measures speed? Temperature. Okay? So that's why a lot of students will ask me, and they'll be like, but, so are we increasing in heat? Yes, my choir students can go, okay? Increasing in heat, okay? Because we're increasing in speed. We're not increasing in mass here, but remember, heat depends on 2 things, temperature and mass, okay? So as we increase temperature, we're increasing that heat, okay? And we start with the different phases. So our first phase is our coldest phase. I want everyone to think about water. When water is in its coldest phase or its lowest temperature, is it a solid, liquid, or gas? Solid. We call it ice, right? So down here at the bottom, the phase that we're at is a solid. Okay? I'm going to zoom in there, okay? The next phase, okay, is going to be a liquid. And what's the hottest phase, you think? Gas. Now, I want you to look at these 3 phases. I've labeled this part of the graph a solid, this one a liquid, and this one a gas. What is happening to the temperature when they're at those phases? What is it doing? It's increasing. How do you know it's increasing? What do you see? What do you see there that shit tells you it's increasing? What's happening? What's happening to the graph? It's going up, okay? So these 2 are where our temperature is increasing. And notice this is all solid, right? This is where all liquid is and all gas. So I'll explain in a minute because it does have to do with those intermolecular forces you guys took the notes on yesterday, okay? And we'll talk about that in just a second. So when we're in a complete all phase, all solid, we will increase in temperature. When we're at all liquid, we increase in temperature. When we're at all gas, we start increasing temperature if we're adding more energy, okay? But what about when we go through a phase change? When we go through a phase change, this is this part of the graph right here. So this is a solid going to a liquid. What do you notice about the temperature in just this section? What is happening there? Is it rising? It's staying the same. How do you know it's staying the same? What do you see? It's a straight line. So it's all at the same temperature, right? When we go through a phase change, like a solid to liquid or a liquid to a gas, the temperature is what we call constant. And that also has to do with our intermolecular forces. So if you were there, you guys should have taken notes on, they're called London dispersion, dipole to dipole, okay, and hydrogen bonding. I am just introducing these to you guys here. You just kind of have to know what they are and what they do, okay? where they're low and where they're high. When we get to bonding, though, we're going to go more in depth with them, okay? Because now you're going to have more knowledge. But intermolecular forces have to do with between molecules. So this right here is a molecule of water, okay? It's just a model. You guys all know it's H2O, right? 2 hydrogen, 1 oxygen, okay? This is a molecule of water, 1. Intermolecular forces is kind of like an interstate. So an interstate, like Interstate 5, goes between states, right? An intermolecular forces is forces between 2 molecules, intermolecular, okay? It's not within the atoms themselves, it's between the actual H2O molecules. So you can see when I put these close together, they are attracted to each other. So that means these guys have an intermolecular force, okay? When we're in a solid, the intermolecular forces are really high because they're really close together like this, okay? When we go to when we go to a liquid, you guys learn that they start to spread out, right? To spread out, we start to break those intermolecular forces, right? Because I'm pushing them apart. This is why when we're in between a solid and a liquid, we're not increasing in temperature or kinetic energy. The reason is the energy we're putting in is going to breaking apart those intermolecular forces to spread those molecules out, okay? The same in when we're at a liquid, so say we're at a liquid, it's kind of like this, kind of spread out, to a gas. When we go from a liquid to a gas, again, the temperature is staying constant because the energy is all going into breaking those intermolecular forces. And when we go from a liquid to a gas, these will split up into separate molecules. So students always think when I go to a gas, I'm actually separating the hydrogen, the oxygen. I'm not. It's still a water molecule, still together. The atoms are still together. It's just now the molecules are separated. Those intermolecular forces are removed, okay? So when we're talking about intermolecular forces, down here when we're going from a solid to liquid, we're breaking those IM forces. I say IM forces because I can't say intermolecular a million times. I'll lose my mind, okay? So here we have so at this point we have high, and I'm just going to write this note, high IM. You can write intermolecular if you like, forces. So when we're in a solid, that's where our IM forces are the highest, okay? They're all kind of grouped up together, right? Right next to each other. They're a big clump. Lots of IM forces in here. When we get to a gas, though, at the end, we are at low IM forces. Okay? Because we broke them here and here. Okay? We added that energy. That energy is going in. One of the concepts you guys are going to have to remember is energy cannot be created or destroyed. Right? It has to go somewhere. If we put it in, it's going to something. So when we look at this phase change and we see that energy is not increasing or decreasing, it's going in to break those intermolecular forces. Okay? We'll go into those much more in depth, but here, that's as far as we're going for now, okay? All right. Put those in there, okay? Now, the other thing that starts happening is pressure and volume. We're going to write the definitions here for pressure and volume. I'm going to write them up here. Pressure is a new thing for you guys. And, of course, just to give you a hint, it's also on your vocabulary list. Okay, pressure is created when molecules collide with each other. Okay, so what happens is pressure is created when molecules actually run into each other. Think about if you have, sometimes I think about 3-year-olds and giving them a Red Bull, lots of energy, right? Let's say I pack a ton of 3-year-olds in here. I am Red Bull, they start running around. Are they going to run into each other more or less because they have so much energy? More. which is going to cause me to get a little upset and them to get a little upset, right? We're increasing that pressure. Okay? You guys can see that increase in pressure. Think about blowing up a balloon. When you blow into a balloon, what happens to it? It expands. Because as you blow in there, you're increasing the amount of stuff in there, okay? And the temperature because you're blowing your hot breath in there, which is causing pressure and it's pushing out on the sides, okay? So pressure is not them pushing out on the sides. That is the effect of pressure, okay? Pressure is actually them running into each other and bouncing off, going to all different directions, okay? So when we talk about that, remember the higher the energy, the more pressure we have, right? So on this graph, when you're looking at which has more energy, a solid or a gas? Gas. How do you know that? They're not all packed together. What else? What tells you the amount of energy that's there? What is that measurement we use to measure energy? Temperature. So a gas, does it have a high temperature or a low temperature? High, which means it also has a, what kind of energy? Kinetic energy, high or low? High. So that means we're also going to have a high pressure. Because now they're moving all over the place, right? Okay. Now, just like a balloon, when you increase the pressure, what happens to the volume of the balloon? Does it increase or decrease? It increases, because remember, we're going to write our definition of volume up here. Volume is the amount of space something occupies. So when you think about a balloon, before you blow it up and increase the pressure, it takes up a little bit of space in the world. When you blow into the balloon, what happens to its volume? How much space is it taking up, more or less, in the world? More. It expands. It takes up more space. So that's why not only will we have, if we have a high pressure, we're going to have a high volume. Okay? It's going to push. It's going to expand, right? Just like a balloon. Just like a gas spreads out. Okay? But when we're down here in the solid, okay, let's say I take all the energy out of my 3-year-olds. They stop running as fast. Are they going to run into each other less or more if they're slowing down? Less. So what's going to happen now to my pressure? Pressure is going to get lower. So down here, we're going to have low pressure. And as you let things out, or let even like a balloon, and you start letting stuff out, what happens to the volume there? It gets less, right? Because if we have a low pressure, then we're going to have a low volume. There's nothing pushing, right? There's nothing pushing. It's what trying to get out, okay? Questions so far? We're also going to learn about some definitions about different things. Some of these you guys might know already, right? When we talk about going from a solid to liquid, say ice is on my table. What do we say it's physically doing? It's melting. So when we're melting, this is what we would call the melting point. Okay? It's where we're melting, right? How about when we go from a liquid to a gas? What is it doing there? What do we say it's doing when it's going from a liquid to a gas? Evaporating. It's evaporating, but what kind of point do you think we say is happening to it? For it to evaporate, this has to melt. This has to... Think about it. When you're at home and you have water, and you know, how do you know it's turning to a gas, water? What do you see? You see steam. When you start seeing steam, what do you say that water is doing? It's boiling. So here is our boiling point. Okay? We also have some other terms we call this. When we're going from a solid to liquid, we have, I'm going to put them right here. When we're going from a solid to liquid, we have a couple names for this. We call this the melting point, or it's melting. When we go back from a liquid to a solid, how about when we go backwards? Freezing. We call it freezing. Because we can go back down. We can decrease the temperature. Okay? And some of you gave this to me right now. When we go from a liquid to a gas, okay, we call that evaporation. Very good. You guys already know that. Okay. Does anyone know what we call going from a gas to a liquid? I heard it there. There you go. It's called condensation. Now, here's one you guys may not know. How about when we go from a solid straight to a gas? And we kind of skip over the liquid part. Anyone know something that does that? You guys have probably seen it. Dry ice. Yes. So does anyone know what dry ice is made of? It's not made of water, just so you know. It's made of what?
Carbon monoxide.
Close. So close. Carbon dioxide. Yes. Luckily, it's not carbon monoxide because we would suffocate, right? We'd kind of suffocate, but it'd be even worse with carbon monoxide. Okay? And so we call this, when this happens, it's called sublimation. Okay? And what that is just so you know, dry ice does not actually skip the liquid phase. The liquid phase happens like this. You have a question? Huh? Okay. Is that better? Yeah? Okay. All right. Sublimation. Okay. All right. Questions on this so far? All right, now we get to do our pictures. We're going to do a picture representation what each little piece looks like. So you have your little pictures here. I want you guys to cut out, not perfectly, okay? You just have to trim these up, make them into separate squares. So I'm just going to, notice I'm not even going to, because we're going to glue those on. Check your glue sticks, make sure they're still good. If they're not good, we can get you some new ones. Okay? We're going to place these little pictures for each of these different phase parts. You should have 5 of here. Okay? All right. Glue. Okay. Now, remember, solids. Are solids close together or far apart? What did you guys learn? They're close together. So we're going to pick, so a solid, if we did a picture representation, would be this one right here. These are extremely close together, right? That would be a picture of a solid. All the atoms are really close. But when we're going from a solid to a liquid, we have 2 phases. Liquids are farther apart, right? We're increasing the energy. We're breaking those IM forces. And so when we're going from a solid to liquid, we would have both represented. You might have, just like you have on my table, a piece of ice with a bunch of water underneath it, right? Notice this is a solid, really close together, all those atoms, and then the liquid is underneath. The next one shows all liquid, which means there's no clumps. There should be no clumps in all the liquid, which it would look like here. Okay. The next one is a liquid to gas. Gas, of course, we're increasing that energy. They're moving faster. They're breaking those IM forces. They're moving farther apart. So we should have some where the molecules are separated out, right? So this would represent a picture of a liquid and a gas together. Okay, notice the top is showing us that those molecules, just like my water molecules here, are splitting apart. And the last one would be all gas, which means we should have separate molecules just flying around. Okay, all right. All right, questions? All right, when you're done with this, you're going to go ahead and put that in your notebook.